Hi, hello everyone. I'm going to share a problem, geometry problem here with some suggestion for exploration. This is actually an old problem that I have come across many years ago, but recently I revisited it and try to find a new way, okay, to see this problem again. And so this is what I want to share with you. It is for me, it is an entirely different ways of seeing this problem, right? But the content itself may not be new to some of you. Here, we'll start with 4 points A, B, C, D, okay, which are all 3 points that you can track freely. And then if you take 2 points each time, okay, then you will have 6 pairs of points, right? And each pairs will give you 1 line and also a midpoint. Or for example, AB here, you have a line AB and also the point P, the midpoint of AB. So altogether, there are 6 pairs of points that you can form. That means there are 6 lines and also 6 midpoints, okay? My suggestion to you here is, if you haven't come across this problem, then you may try to move around the point A, B, C, D to see whether the 6 midpoints, which are in orange, okay, can be put into one circle, right? That means all the 6 orange points will lie on one circle at the same time, okay? And maybe you can pause here and then try to go ahead and follow my links below, okay? And try to have a look and see whether you can find some way to arrange the 4 points A, B, C, D. And also try to be, maybe find more general conditions or not simply very specific ones. Okay, after your trial, then you can continue, okay, to follow or maybe try to see what I suggest to do next. Okay, suppose you have tried it already, and maybe this is something that you may have found, okay? For example, you can put the point here. Okay, let's say if ABC form an equilateral triangle, then it's quite symmetric, okay? Then probably you can get a circle around the 6 points here, right, in this way. But even if ABC is not an equilateral triangle, you can still have some way to make it. Okay? For example, this one. It will be quite close. Okay? Now, if you want to check whether it really passes through a circle, then you can try to join, let's say, 3 of the points. All right, and then adjust it a little bit, and then you'll find that finally you can get all the 6 points on one circle, something like this. But what is the general condition I have leading to this 6 points lying on one circle? If you try to spend some time to continue to explore, okay, then you may find that it seems that D was the ortho center of the triangle, right? And that means you will see 3 pairs of perpendicular sides here in this picture. Okay, this is the way I color the side. Okay, that's why I try to put the sides into 3 colors. Okay, and to let you distinguish them. So you can see that the each pairs of lines of the same colors are perpendicular now. So for example, these 2 lines and these 2 green lines and then 2 blue lines below. Okay, and so now you may have come across this properties or theorems before. Okay, actually this is called a line point circle because you can also mark the perpendicular, foot of perpendicular of each pair. And then you see that they are also lying on the same circle. So this is called a line point circle. You want to have a check. But my interest here is to find a way to look at this configuration and try to help us to see more clearly why these 6 points will form a circle in a particular case. Okay, and this is how I try to continue. If you're interested, you may also have a look on your own and try to think about what else you can observe in this figure, or what question you may ask, and then later on, or maybe some explanation you want to give due to your findings. Okay, and after your own trial, then you may follow the rest of my video to see my sharing as well. Okay, all right. Okay, I suppose maybe you have already done your own trial, then this is the things I want to continue to share with you. So here in this figure, you'll find that it is another file I prepared with a little bit more information provided, okay? Because in my exploration, I try to distinguish the 6 points in different ways, okay? According to the original pairs of line that I highlighted in different colors. Okay, so this is the way I see the 6 points, okay? And basically, because they are all midpoints of certain size or segments, okay? And so I remember what I know about the midpoints of triangles or quadrilaterals. Particularly one I'm quite interested is about the midpoints of 4 sides of quadrilaterals, okay? And that is the way I see this diagram, which I think can be interesting, and then try to go on to figure out whether this way of looking at the diagram will be useful. Okay, so if you go back to my table above, you can see I distinguish 4 pairs of segments each time. Sorry, 3 pairs. I have 3 pairs of segments. Each segment actually consists of 2 pairs of points. You can also see that it is the way I distinguish or partition the 4 points. Okay, so the first pair is A, B, C, D, and then the second pair is A, C, B, D, and then A, D, B, C. Okay, that means there's just different ways of separating the 4 points into 2 groups. And for each pairs of lines, I mark it for the same color. And you can also find the intersections for each pairs as well. So if you show the intersection, then you will see the intersections are here in the diagram. Okay, the intersection may be useful later. And then the midpoints, similarly, the midpoints are also put into 3 groups. Okay, the first group PQ correspond to the 2 sides A, B, and C, D. And then the remaining 4 will form a parallelogram. Okay, now you may not readily notice why it is a parallelogram. Okay, maybe I take out the circle. But this is actually based on what we know about midpoint theorems. Okay, so you can have a check, try to notice that the sides of this parallelogram RT and SUs are parallel to these 2 sides A, B, and CD. Okay, so you can figure out a little bit more why it is like this. And similarly, if you look at the second pair, okay, RS are the points on these 2 pairs of sides, but the remaining 4 will form a quadrilateral, which is also a parallelogram, which is sides parallel to AC and BD. Okay, the same reason, because of the midpoint theorem, that you can always prove that this is a parallelogram. Now, what interests me is that actually that means identify 3 parallelograms out of the 6 points. Okay, you just take away 2 points each time, then the remaining 4 points will form a parallelogram. And I also distinguish the parallelogram according to their diagonals. So the first one, RTSU, we have the diagonals, RS and TU. Okay, so RS, TU here are the diagonals. Okay, and so similarly, the other one, the second parallelogram, we have the other diagonal PQ and TU corresponding to the other 2 pairs of points that you can identify, okay, from another set of lines. And now you will find that the diagonals actually are interrelated, because actually any 2 of this parallelogram always share one of these diagonals. For example, these 2 will share the same diagonal PQ. Okay, so I would say that these are 3 interlocks or interlinked parallelogram, and any 2 of them, any 2 of them will share one particular diagonals. Okay, that is what I noticed. It's quite interesting. And in fact, all the 3 diagonals, therefore, because they are diagonals of parallelogram, therefore, you'll also find that the 3 diagonals also meet at 1 point. Okay. Okay, there's something else I just noticed. All right, now go back to the problem about the circle. In what way the 6 midpoints will form a circle or will lie on one circle? Okay, and you find that actually when they really form a circle, okay, actually you can draw 3 points for a circle by 3 points, just like this. Okay, and then you move to other 3 points on the circle, and then you will find that the parallelogram will nicely form 3 rectangles, which also makes sense, okay? Because in general, a parallelogram cannot be concyclic unless that parallelogram is a rectangle, okay? Now, if you accept that the 3 quadrilaterals here must be parallelogram, then the only way for them to be put on the circle is to have each one of them to be a rectangle. But how can they be a rectangle? If you look at the first, any one of this, for example, RTSU, since this parallelogram have the size parallel to AB and CD, okay? So the only way to make them a rectangle is to make sure AB and CD are perpendicular. So I try to make AB, CD perpendicular, for example. Once they are perpendicular, then it must be a rectangle, although it may not be lying on this particular circle, okay? However, if you want it to be on circle, then at least it must be a rectangle, right? That means AB, and CD must be perpendicular. So similarly, if you want another quadrilaterals, parallelogram to be concyclic, then you have to make sure another pair of sides, ACBD are perpendicular, okay? So that is the only way to make them concyclic. Now, and go back to these 3 parallelograms. So that means making one of them to be rectangle is not that difficult. You just make sure 2 sides, this 2 sides of same color are perpendicular, right? And then if you make 2 of them a rectangle at the same time, then you have to make 2 pairs of sides perpendicular. Now, which is still not difficult actually, okay? In fact, you can guarantee that you can always do so, right? And then by the knowledge of the orthocenter, then you may also realize that when you make 2 pairs of colored sides perpendicular, the remaining pairs of the colored lines should also be perpendicular at the same time, okay? And in fact, if you make 2 quadrilaterals, for example, these 2 parallelogram being rectangles, since they share particular diagonals, okay, then you'll find that that means the consequence is that all the 3 diagonals will be the same length and also will be the diameter of a particular circle, okay? And it also means that the other quadrilateral will be forced to be a rectangle at the same time. That means the third one, because we also know that PQ and RS from the above deduction, PQ and RS are also equal, and they're also meeting at the midpoint, right? Being the diameter of the same circle. Okay, that means the conclusion is that if you make any 2 of these parallelograms a rectangle, then the third one must also be a rectangle at the same time. Okay, and that explains why. Okay, if D is the orthocenter of the triangle ABC, or you say that ABCD, these 4 points form an orthocentric sets. Okay, then the 6 midpoints will automatically fall on one single circle. Okay, and finally, according to what traditionally we know about a 9-point circle, the foot of the perpendicular will also be on the same circle, okay, which is not difficult to prove, just because now we know why the other points are perpendicular, right, based on the rectangles that we identify. Then we can see that, for example, TU is a diagonal, and then TZU, okay, while forming a right angle, then should fall on the circle as well. Similarly, if you identify the other diagonal or diameters, okay, of the circle, then you can also explain why the foot of perpendicular should also be lying on the same circle. Okay, so that is the way I see this particular relation. And to me, it's another way of looking at the situations, right, which I think can be quite interesting. And finally, I also like to share one extra observation I have, because while working on this problem, then I realized that actually the 6 points here, although generally they may not be lying on the circle. However, if you look at the, if you join this like this, this is to me a bonus, right? Because now I realize that even though in general it may not be lying on the same circle, however, this 6 point should always form a hexagon, right, with parallel opposite sides, parallel and equal opposite sides, okay, which may not be obvious at the beginning, okay, but now we can revisit it in this way. And even more amazing to me is that since when I try to explore this problem, I try to construct a circle through 3 particular points to check whether they are falling on a circle. Then for example, in this GeoGebra apps, actually you can create generally a convex, right, based on 5 points. Then why not we just choose any 5 points to create a convex instead of just a circle? And what's surprising to me is that the 6 point automatically fall on the same convex, okay? And that is what you can see now, okay? So that means in general, the 6 points are lying on the same, for example, in this case, an ellipse. Only in a particular situation, the ellipse will be specifically a circle. And in fact, if you move it out, then the convex will be perhaps a hyperbola, okay? But there you can see before the 6 points are still falling on the same convex, right? While now we see that the circle is just a special case, okay? I think there will be quite a lot to be further explored if you follow this direction. To me, I believe that this is very much related to descriptive geometry, which I think I have to find time to take out more if I want to investigate this direction. Oh, so I hope that you enjoy this exploration together with me, and also appreciate maybe some new way of looking at old problem. Of course, I don't know exactly whether this is a tiny new way to every one of you, okay? But I hope that this sharing will be interesting to some of you as well. Okay, thank you for following and listening to my sharing and explanation here.